Our understanding of reality rests on a single explosive moment, the Big Bang. It describes a point of unimaginable density and heat, when all of space, time and matter expanded from a singularity nearly 13.8 billion years ago. This event set galaxies in motion, forged the elements, and shaped the cosmic background glow we still detect today. For decades, it has been the cornerstone of modern cosmology, the alpha point of our cosmic story. But what if it's not the whole story? What if the Big Bang wasn't a true beginning, but merely a transition, an echo of catastrophe in another, older reality? There is a theory, a fringe yet increasingly discussed idea, grounded in the strange mathematics of quantum physics, that suggests the birth of our universe wasn't an act of creation, but a transformation inside one of nature's most violent objects. If this theory is right, then the vast, expanding cosmos we call home may not be what it seems. We could be living inside a black hole. The story of the Big Bang is elegant. It explains the expansion of the universe, the existence of the cosmic microwave background radiation, and the abundance of light elements we observe in the cosmos. Yet, at its very heart, at time zero, it contains a monster, a singularity. This is a word physicists use to describe a point of infinite density, infinite temperature, and infinitely small size. It is also the very point where the law of physics breaks down and the smooth geometric equations of Albert Einstein's general relativity cease to make sense. For many scientists, a singularity isn't a real feature of the universe, but evidence that our theories break down. It's a mathematical ghost haunting the house of cosmology, hinting that general relativity alone can't fully explain gravity in the most extreme realms. Those realms appear both at the birth of a universe and in the heart of a black hole. But first, let's take a step back. What exactly is a black hole? It's the dense, invisible remnant left behind when the universe's most massive stars reach the end of their lives. Throughout its existence, a giant star maintains a delicate balance. Deep in its core, intense heat and pressure drive nuclear fusion, fusing hydrogen into helium and releasing tremendous energy. This outward radiation pushes back against the star's immense gravity, creating a stable equilibrium that lasts for millions of years. However, this fuel is finite. When the hydrogen runs out, the star begins fusing heavier elements, helium into carbon, carbon into neon, and so on, in a series of concentric shells like a cosmic onion. This process culminates in the creation of iron. Here, the star meets its doom. Unlike the fusion of lighter elements, creating elements heavier than iron consumes energy rather than releasing it. The star's internal engine suddenly shuts off. With the outward pressure gone, gravity wins instantly and catastrophically. The core collapses in less than a second, crushing down with unimaginable force. The star's outer layers rain down upon this imploding core, then rebound in a titanic explosion known as a supernova, blasting most of the star's material into space. If the mass of the leftover core is great enough, roughly more than 3 times the mass of our Sun, no known force in the universe can halt its continued collapse. This is where our journey truly begins, because this process leads to the creation of a singularity, the same mathematical paradox found at the heart of the Big Bang. Just like the proposed origin of our universe, a black hole is predicted by general relativity to contain a point of infinite density where the known laws of physics crumble. The boundary marking the point of no return is called the event horizon. Crossing it is a one-way trip into this gravitational abyss. Do you see the parallel? The two most extreme phenomena known to physics, the birth of our universe and the death of a massive star, both lead to the same mathematical impossibility. This has led a handful of bold physicists to ask a radical question. Are they somehow the same thing? Could the singularity of the Big Bang be a cosmic illusion, hiding a more profound truth about our origin? This is the central claim of a set of ideas known as black hole cosmology. It proposes that our universe is the interior of a black hole that exists in a much larger parent universe. From the outside, it is a black hole, but from the inside, it is an entire expanding cosmos. The Big Bang in this view was not a singular moment of creation, but a big bounce, the moment that matter, collapsing inside a black hole, was saved from oblivion by the strange and powerful rules of the quantum world. For a universe to be born from within a black hole, it must sidestep the fate of infinite collapse predicted by Einstein's theory and avoid becoming a singularity. To do this, it needs a new repulsive force that can stand against the crushing might of gravity at microscopic scales. This is where quantum mechanics enters the stage. The Pauli exclusion principle is a cornerstone of quantum mechanics, a fundamental rule that says two fermions, such as electrons, protons, or neutrons, cannot occupy the same quantum state at the same time. In simpler terms, it's as if each particle has a reserved seat defined by its unique energy, spin, and other quantum properties. Once that seat is taken, no other identical particle can sit there, forcing newcomers to occupy higher and higher energy levels instead. This seemingly abstract rule has profound consequences. When matter is squeezed closer together, the available seats for fermions run out quickly. As particles are forced into higher energy states, they generate a powerful outward push known as degeneracy pressure, a kind of quantum resistance against being packed too tightly. It's this pressure that holds up white dwarfs and neutron stars against their own crushing gravity, preventing them from collapsing further. And intriguingly, some physicists believe this principle might play an even grander role. They propose that the same quantum rule, which shapes the structure of atoms and the stability of matter around us, could provide the ultimate resistance against a singularity. In the extreme densities inside a black hole, degeneracy pressure could become strong enough to halt the collapse entirely, triggering a rebound that gives birth to a new cosmos, a universe rising from the ashes of a dying star. But if this hypothesis is correct, what does it mean for us? What would it be like to live inside a black hole? The answer, unsettlingly, is that it would be exactly like this: the expanding universe we see, the galaxies flying apart from one another, the cosmic microwave background radiation painting the sky. All of it is consistent with the picture of a universe that erupted from a bounce within an event horizon. We wouldn't feel any sense of confinement. The interior of the kind of black hole needed to house our universe would be gargantuan, trillions of light years across. The event horizon, the point of no return, would be so far away that it would lie beyond our own cosmic horizon, the boundary of the observable universe. We could never reach it. We could never even see it. From our perspective, the laws of physics would be consistent and unwavering. Gravity would still pull us to the ground, light would still travel at the speed of light, and stars would still burn through their fuel. There would be no sign, no immediate clue that our entire existence is playing out within the gravitational confines of another, larger world. We would be like fish who have never conceived of the world outside the ocean. Our universe would feel complete, total, and absolute. Yet we would be prisoners, inhabitants of the ultimate cosmic prison, a jail whose bars are woven from the fabric of space-time itself. No matter how advanced our technology becomes, no matter how fast our ships fly, we could never escape the bounds of the parent black hole's event horizon. The very expansion of our own space, which we perceive as the aftermath of the Big Bang, would be carrying us deeper into the black hole's interior. We are not just living inside a black hole, we are, in a very real sense, falling through it. But this falling raises a strange question about time. Inside a black hole's event horizon, scientists think space and time swap roles. The singularity isn't a place you can avoid by moving sideways. It becomes a moment in your future that you must reach, just like you can't stop time from moving forward. If that's true, how can a universe inside a black hole last for billions of years instead of ending instantly? The idea of a bounce offers an answer. Instead of ending in a singularity, the collapse could stop and explode outward again, starting a new universe. This bounce wouldn't just be a change in space, it would create a whole new timeline. From inside the new universe, time would flow outward from that bounce, the same way our time flows forward from the Big Bang. Our arrow of time would simply be moving away from that cosmic rebound, beginning a brand new history after the end of the previous one. This connection also raises a profound question. If our universe was born inside a parent black hole, do we carry its traits? While the event horizon blocks any direct view of the outside, physics insists there must still be a link. For example, the total mass and energy in our universe would be inherited from the mass of the star that collapsed to create our cosmic parent. But the connection might be even more dynamic. Some physicists have speculated that the slow evaporation of our parent black hole through Hawking radiation could leave traces inside our universe. As the parent black hole gradually loses energy back into its own universe, this loss might appear to us as a gentle, persistent outward force. Remarkably, this force could be indistinguishable from the mysterious dark energy that's causing our own cosmic expansion to speed up. If so, the greatest puzzle in modern cosmology, dark energy, could be the faint, ghostly whisper of our parent universe, hinting that our cosmic prison is slowly fading away. This idea radically reframes our place in the cosmos. The Copernican revolution taught us that the Earth is not the center of the solar system. Later, we learned our solar system is just a speck in the Milky Way, which itself is one of hundreds of billions of galaxies. Black hole cosmology represents the next, and perhaps final, step in this great cosmic demotion. It suggests that our entire universe, in all its incomprehensible vastness, might be nothing more than a single, transient particle inside a much larger reality, a footnote in a cosmic story to which we are not privy. This leads to a chilling vision of an infinite, nested reality, a cosmic matryoshka doll of universes within universes. The black holes in our own universe, from the supermassive giants at the heart of galaxies to the smaller, stellar mass ones, could right now be birthing their own baby universes, each one a self-contained reality whose inhabitants would have no idea of their origins, just as we have no idea of ours. The physicist Lee Smolin took this idea a step further with his theory of cosmological natural selection. He proposed that universes reproduce through black holes. A universe whose physical constants are tuned to produce lots of black holes will have lots of children. Over cosmic time, this process would favor universes with laws like our own, where the formation of stars and black holes is commonplace. Our existence in this view is not a lucky accident, but the result of a cosmic evolutionary pressure. We live in a universe that is good at making black holes, because we are the product of one. The mechanics of this cosmic evolution mirror the principles of biology. The genes of a universe are its fundamental constants: the speed of light, the strength of gravity, the charge of an electron. According to Smolin's hypothesis, when a new universe is born from a black hole bounce, these constants may undergo small, random changes, much like genetic mutations. Now, imagine a universe whose constants change in a way that makes it difficult to form large stars. That universe would produce few, if any, black holes, and thus have no offspring. It would be an evolutionary dead end. But a universe that mutates to have laws that are exceptionally good at creating massive stars will birth countless black holes, and therefore countless new universes. Each of those new universes will carry similar, slightly mutated genes. Over eons of cosmic time, this process would naturally select for universes whose physical laws, like ours, are perfectly fine-tuned for the creation of stars and black holes. Our seemingly miraculous fine-tuning would be no miracle at all, but rather the predictable outcome of cosmic survival of the fittest. But the idea that our entire reality is a sealed-off bubble, a region of space-time from which there is no exit, is a terrifying thought. The sky above us, which has always been a symbol of the infinite, becomes a ceiling. The cosmic horizon becomes the wall of our cell. This sense of confinement is coupled with a deep and unsettling fragility. Black holes, according to the work of the late Stephen Hawking, are not eternal. They evaporate. Over unimaginably long timescales, they leak energy back into their parent universe. A black hole is not a permanent fixture, it has a lifespan. So what happens to the universe inside it as it slowly dies? Does our reality slowly fade as its parent bleeds away? Do the fundamental constants of our physics shift as the mass and energy of the parent black hole change? No one knows. The theory is not yet complete enough to provide an answer. We are left floating in a state of cosmic uncertainty, inhabitants of a house whose foundations could be slowly dissolving without our knowledge. Perhaps the most profound dread comes from the theory's implications for meaning and purpose. If our universe was not a singular, divine act of creation, but simply one link in an endless mechanical chain of cosmic birth and death, what does that say about us? Our struggles, our triumphs, our art, our love, all of it plays out on a temporary stage, inside a temporary bubble that is itself just one of countless others. There is no ultimate beginning and no final end. only an infinite cycle of universes being born from the collapse of matter in a parent universe, and in turn, giving birth to new universes through their own black holes. It's a cosmic Ouroboros, the snake eating its own tail for eternity. This vision can be seen as profoundly nihilistic. It suggests a reality devoid of any inherent purpose, a grand, unthinking machine endlessly recycling itself. Our existence is not a story with a beginning, middle, and end, but just a single meaningless vibration in an infinite, indifferent hum. The search for an echo in the dark. But a theory, no matter how elegant or existentially terrifying, is just a story without evidence. The standard model of cosmology, which includes the Big Bang and a subsequent period of rapid expansion known as inflation, is the reigning champion because it makes predictions that have been stunningly confirmed by observation. For black hole cosmology to be taken seriously as a replacement, it must do more than just solve the singularity problem. It must explain the universe we see at least as well as the current model, and ideally, make a unique, testable prediction that could distinguish it from the competition. So, are there any breadcrumbs? Any clues left over from our universe's violent birth that could point to a black hole origin? The answer may have arrived from the James Webb Space Telescope. In a 2025 study published in the monthly notices of the Royal Astronomical Society, a team led by researcher Lior Shamir analyzed hundreds of early galaxies and discovered a stunning anomaly. Their rotation isn't random. Roughly 2/3 of the observed galaxies spin in one direction, while only 1/3 spin in the other. This profound asymmetry defies the standard assumption that the universe should be isotropic, or the same in all directions. According to Shamir, the simplest explanation is that the universe itself was born rotating, a characteristic it would have inherited if it formed inside a spinning black hole. This finding provides the first observational evidence that our cosmos might possess a large-scale structure, a cosmological scale axis, hinting that it retains a memory of its violent spinning birth. Furthermore, some models suggest our universe might retain a slight memory of its confinement in another manner. This could manifest as a tiny positive curvature to spacetime. For decades, astronomers have been trying to measure the geometry of our universe. A flat universe would expand forever. A negatively curved or open universe would also expand forever. But a positively curved or closed universe would eventually collapse back in on itself. A universe born inside a black hole might be expected to be closed. So far, our best measurements, primarily from the cosmic microwave background radiation captured by the Planck satellite, show the universe to be almost perfectly flat. But there is still room for a very slight curvature within the margins of error. Future telescopes and CMB observations will refine this measurement, and if they detect a slight positive curvature, it would be a significant point in favor of a bounce. Beyond the overall shape of the universe, the true smoking gun may lie in the primordial gravitational waves, ripples in space-time left over from the universe's first moments. The standard inflationary model predicts a very specific spectrum of these gravitational waves. However, some bounce models predict a different spectrum, or in certain cases, a much weaker signal that would be undetectable. If we were to detect a specific type of gravitational wave background that matches the predictions of a bounce, it would be a monumental discovery. Furthermore, scientists are hunting for subtle patterns and temperature anomalies in the cosmic microwave background. A bounce might have allowed for echoes or statistical traces from the pre-bounce, contracting universe to survive, leaving large-scale correlations in the sky that simple inflationary models cannot easily explain. Finding such a pattern would be like discovering a cosmic fossil from a reality that existed before our own. Other potential signatures might be hidden in the subtle temperature fluctuations of the cosmic microwave background, or in the distribution of galaxies on the largest scales. But the challenges are immense. The greatest hurdle is the most obvious one. The parent universe is, by definition, beyond our reach. The event horizon of our parent black hole acts as an impenetrable information barrier. We cannot see out. We are trying to understand the nature of the room we are in, without ever being able to see the house it is built into. This leaves the theory in a state of speculative beauty. It is criticized for its lack of direct evidence, while the standard inflationary Big Bang model, for all its problems with the initial singularity, works exceptionally well as a predictive framework. Black hole cosmology offers a more complete, more aesthetically pleasing origin story that eliminates the paradox of the singularity, but it has yet to provide the concrete, observational proof needed to overthrow the established paradigm. The search continues. Scientists are pushing the boundaries of both theory and observation, developing more sophisticated models of a bouncing cosmos, and designing new experiments that can probe the early universe with ever greater precision. Perhaps one day, a subtle anomaly in the cosmic background, a strange pattern in the arrangement of galaxies, or even a breakthrough in our understanding of quantum gravity will provide the definitive clue. Until then, we are left to wonder. We look up at the night sky, at the countless points of light that represent entire galaxies, and we must confront a disquieting possibility. We may not be looking out into the infinite, but merely at the distant glittering walls of our own cosmic prison. The beginning was not a bang, it was a bounce. And our universe is not everything. It is just one of many, born in the dark, silent heart of a black hole.